Hello and welcome to lesson 4.3. This lesson we're calling it quadratic methods because what we're hoping to use is a lot of the stuff we learned to kind of solve more difficult polynomials. So one of the things we're really going to focus on at first in this lesson is that if I'm looking at something like this, x to the fourth power minus 13x squared plus 36 equals 0. And I say, could you solve this for x? The first thing I want you to say is, no, we've only done up to x squared. This looks too crazy. And I'll say, good, 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 good. Good thinking. But this looks so similar. This looks so very much like a trinomial that we could factor and solve. Well, I'll go ahead and tell you that we can. If we go ahead and instead of writing this x to the fourth, let's write this as x squared squared. That is the same thing as x to the fourth. Would you agree? Minus 13, and we'll go ahead and just call this x squared. We'll put it in parentheses. Plus 36 equals 0. I have done nothing more than rewritten x to the fourth as x squared squared, and nothing but put parentheses around the x squared part. Now, you don't have to do this part, but this part helps people visualize it. If I let another letter, let's just say, I don't know, p, let's let p equal x squared. Just for visual sake. You do not have to do this. We could go ahead and jump into getting the answers. But if I did that and I replaced all the x squareds with p, replace this x squared with p, I would have p squared minus 13p plus 36 equals 0. And you would say, well, this we can do. This is very easily factorable. We've been doing this for weeks now. I could rewrite this. I could factor this easily. Let's see, what two numbers multiply to 36 and add to negative 13? Okay, well, we can handle that. Let's see, that would be let's see, a negative 9 and a negative 4. That multiplies to positive 36 and adds, yeah. Now, that's great and all, but we're not doing this problem with p. We're doing this problem with x's, and p is not what we're working with. These p stands for x squareds. And so if I replace them back now, I will see that I have something entirely, well, interesting. So I could have maybe factored this, just realizing that when I have a fourth power, I can't think of it as a squared. And so I have x squared minus 9, x squared minus 4. Wait a second, both of those things factor. So I can continue to use my quadratic ideas that we've studied in this course, my quadratic methods, and I could factor each of these. X squared minus 9, that's a perfect square minus a perfect square. Oh, I forgot to put the number. But x squared minus 9 factors into x plus 3 and x minus 3. X squared minus 4 factors into x plus 2 and x minus 2. Oh, and I have a bunch of factors multiplied equal to 0. I can still apply my same principles where I'm going to let each factor equal 0. And I can solve each one to get, in this case, not 2, but 4 different solutions. Okay. And hopefully you're gifted enough that you could solve these in your head. If you take the time to solve them, you subtract the 3 over and you'd get x equals to negative 3. And this one you'd add the 3 over, you get positive 3. Here you'd subtract the 2 over and get negative 2. Here you add the 2 over and get positive 2. And so there, I got 4 solutions for this one. If you go back to the original and plug these in, these should all work. Really interesting. Now, there's some theory here you may want to spend some time dabbling in, but often we can look at our highest degree exponent and say, I bet I'm going to have that many solutions. Fourth, I had 4 solutions. Now, whether they're all real or complex or not is a completely different story. Okay. And I'll show you that in the next example. But to solve these things, we should be able to go out of our way using all the quadratic methods that we know to come upon these solutions. So let's jump into another one then. What if I were to ask you to solve something like this? Let me find my example. It is x to the fourth minus 3x squared minus 4 equals 0. And once again, you could think of this as x squared squared and substitute it for p, but hopefully you'll say, okay, I think I can save myself some time this time and go ahead and try to factor it and know that these leading two terms are probably going to be x squared. Let's see if we could factor this. So numbers that multiply to -4 and add to +3. Oh, that'd be -4 and a +1. Nice. Oh, wait, this one factors some more. I can factor a perfect square minus a perfect square. So that'd be x plus 2 and x minus 2. Now, sadly, this one, x squared plus 1, we don't have any special factor for sum of squares. So that one doesn't factor. But I have three different pieces here, all multiplied to equal 0. So I should be able to, in theory, say, okay, let's set each one equal to 0 and solve. Okay. Now, the only interesting one's going to be this last one, because how do I want to solve it? Well, let's come back to it. Let's go ahead and get the other answers here. So if I solve this one, I'm going to get x equals -2. Solve this one, I'm going to get x equals +2. I guess since I don't know what I'm doing with the last one yet, I'll write it as its own separate x equals +2. Now, what am I going to do here? Well, let's use any of our quadratic methods to solve this. So I could use a quadratic formula. I could do, let's do the thing where we move everything over and just square root it. So subtract 1 from both sides. So then x squared equals -1. And then we will square root both sides. Square root, square root. Okay. Now we're going to remember that this is going to be the positive and the negative of this. So x, because the square and the square root cancel, is equal to the positive and the negative of this, square root of -1. Wait, we know what that is. That's I. So we're going to have I and negative I. So we got four solutions again. We got 2, -2, I, and negative I. Because remember from our last lesson, the square root of -1 is just I. Okay, cool. So we got four solutions. Two of them are real numbers. Two of them are complex numbers. That's interesting. So hopefully you see that I can still solve these things when I have anything in this kind of pattern. I can just try with the x to the fourth and x squared, and those are my only two variables. I should try these kind of methods of solving it. If I have much more mess, what I'm going to end up getting into is having to find one factor and do long division or synthetic division, and that gets messy. We're not going to cover that right now at this time, or maybe not at all in this course. Okay. So now this is intriguing. So I feel like I could always come up with four answers, but it might be useful to know how many are real numbers and how many are complex. And guess what? There is an easy way to know this. So there is something called the discriminant. Okay? If you don't know what the discriminant is, we've been using it for a few lessons, or at least one lesson. If you look at the quadratic formula, okay, this is not the discriminant, but if you look at the quadratic formula, piece of this thing is the discriminant. I'll tell you which piece after I finish writing it. It takes a while to write it. The piece underneath the radical. B squared minus 4 times A times C. What the discriminant does is if I go ahead and just plug things in, I'm going to have one of three things happen. I could get that it's positive, I could get that it's negative, or I could get that it is equal to 0, neither positive nor negative, and all of these three things mean something different. If it's positive, the square root thing that I'm working with is going to give me two real solutions. If it's negative, I'm going to end up with two complex or imaginary solutions. Two of the I type things. And finally, if it's equal to 0, I'm going to end up with one of each, one real solution. Okay. So thinking back to our examples, this is talking about whenever I factored like that second example and I had, what was it? X squared plus 1. If I wanted to know how many real solutions I could get from this thing, I could plug this into the discriminant formula here and see whether it's positive, negative, or 0. Well, there's no b term. This is x squared plus 0x plus 1. And so it's not that entertaining because b squared would be 0 squared minus 4 times a would be 1 times c would be 1. So it'd just be 0 minus 4. Oh, well, that's negative 4, which means I would get two complex numbers. Did I get two complex numbers from solving this x squared plus 1 part? Yeah, I did. I got negative I and positive I. Okay, cool. So, in a more interesting batch, then, diving away, kind of getting away from solving those with big exponents, if I just wanted to solve something like this, x squared plus 2x plus 1. I said, let's go to solve it. Before I start to solve it, I'm kind of curious, am I going to get one real number, two real numbers, or two complex numbers? All I need to do is look at the discriminant. So I say, okay, b squared, that would be 2 squared, minus 4 times a, so no a shown here, so it's 1, times c, which is 1. Okay, what's that going to be? That's going to be 2 squared is 4, minus 4 times 1 is 4. 4 minus 4 is 0. So how many solutions am I going to get here? I'm going to get one real solution. Now, you don't, let's see for fun. If I tried to factor this, what do I want to do? We could use the quadratic formula to solve this. So negative b plus or minus the square root of, guess what? We already did. The determinant is 0 divided by, and then 2 times a is just 2 times 1. And so what I get here is negative 2 divided by 2, negative 1. Huh, okay, interesting. Whether I add or subtract 0, I get negative 1 either way, right? All right, so I got 0, I only got one solution. Interesting. What that means on the graph, so whenever we're setting these things equal to 0 and solving it, what that means on the graph is that the parabola, these are parabola shapes. This is whichever way you draw it, means that it's just touching 0 at one point. Whether it's concave up or concave down, it's touching the x-axis just at one point. Okay, just connecting the graph visuals to these. Or if you get a negative 1 and two complex, no real solutions, what that one means is it's not crossing at all. It's like down here. There's nowhere where it hits a height of 0. Okay. And when you get 2, that's when it's crossing it twice like that. If any of this confuses you, ignore it for now. That's kind of some bonus extra kind of like just extra insight for people that are wanting to dig a little deeper. Let's just do one more example. You tell me how many solutions I'll have or what type of solutions I'll have. Okay. So we'll use the discriminant to see how many solutions I'll get. So 2x squared minus 7x minus 4 equals 0. So we'll use the discriminant. Remember, that's just the b squared minus 4 times a times c part. All right, so b squared, so negative 7 squared is 49 minus 4. A is 2, so times 2. And b is negative 4. So 49. All right, 4 times 2 times 4. Well, I have a negative times a negative. That's going to end up being a positive or a plus. 4 times 4 is 16 times 2 is 32. So this thing is a positive. things greater than or equal to 0. It's a positive, right? So what that means is when you solve this, I'm going to get two real solutions. Okay, now all I'm asking you to do for these type of the homework is I'm going to have you just tell me how many real solutions you have. So you're going to look at this, plug in into the discriminant formula, and tell me if it's positive, you get two real solutions, or if it's negative, or if it's 0. Are you getting one real solution or no real solutions? How many real solutions are you getting? That's all you're doing with that. That's not super difficult. So kind of two things here in quadratic methods. Let's see if we can solve these kind of in this special form with x to the fourth, and we'll get four solutions. And then let's see if you can look at a plain uh, polynomial and tell me how many real answers I'm going to get. Two reals, one real, or no reals, two complexes. Okay, that's all I'm asking for you right now at this stage.